Aaliyah and Landon are here. Hi, guys.
Hello.
Hello.
Ben is here. Let's see. I'm going to show you guys something awesome to start this off. And if you're late, then you just missed it. So I'm sharing a screen with you, Gal, and I'm going to show you what I was doing 20 seconds ago. I'm going into my architecture file, into completed drawings, and I was working on Geigel's house, and I'm going to show you roof beam 3. So one of the main things that I do when I'm drawing house plans is design beams. And what I'm going to teach you today, as we leave chapter 2, which is where we resolved complicated numbers of forces, ultimately using the principle of breaking one force at an angle into its component X and Y ports and then adding them all together to see what the result was. We're going to switch now to something called moment. And I just want you to see it right here. So this is a printout of something I've got to turn into the city. And notice it says right there that the moment on this beam, and there's a picture of it up here, the moment on that beam is 10,859 pounds. That's the moment that is on that beam based on the load that's above it. Notice, and we'll get into this later in this class, but see how there's a kind of a tan colored beam and it's sitting on a couple of posts, these two yellow posts, and then you got these forces up here. Notice there's a 1 and a 0, and down here it says 0 is the self weight. In other words, just the weight of the beam itself. A bridge actually weighs a ton all by itself before you put any cars on it. So you got a beam that has weight, and then you also have the one here is the standard load of the floor. So floor weight is a certain weight, and so that's the forces that are put on that. Notice, to get into something we'll get into the future, notice there's not just 1 or 2 arrows there. There's tons of them everywhere. There's arrows everywhere, and you sort of got to figure out what that's going to mean. And does it make sense that if you put that weight on that beam, that the beam wants to bow down in the middle? And notice it tells me right here, maximum deflection of that beam is 1/2 inch. In other words, this calculation tells me that beam's only going to bow down 1/2 inch under the load that's on it, which is good. That's not very much. If it's more than 1 inch, the beam is considered to fail. So we certainly don't want it to bow down so much it breaks. But what causes that is, well, what's called moment. Effectively, all of these pushing down, if you were to sort of cut this beam in half and just look at the left side, does it make sense that from here to the middle, that whole beam just wants to kind of go and rotate down? Moment, or what you may have seen in physics called torque, torque is the desire something has to rotate. And so that rotation is what causes the bending in that beam, which is what we've got to make sure the beam can handle. So this is kind of a key description. So notice 10,859 pounds of moment. Let me show you one other quick thing here, if I can find it fast, that is. I'm assuming I have a copy of that in my engineering files. Doesn't look like I do. Yes, I do. So Boise Cascade puts out the beams that I spec, and this is a little chart of them. And just since we're in here, this is kind of cool. That beam right there is called a Versalam beam. It's just sandwiches of 1/10 inch thick wood that's all glued together. So that's what I'm usually specifying for a house. But I just want to show you this little chart that if you're doing this by hand, I was doing it using a computer program, so I didn't actually have to know very much. Somewhere in here, I can't remember what page it's on. Pages and pages of tables and so forth. hopefully when you look at that, you think, slow down, I want to see all that, because you're an engineer. That's what engineers want to do. Let's see, that's BCIs. We need beams. There we go. We're getting warm now. There we go. Make bigger. See this statement right here, allowable moment. In other words, can you picture if you put it too small of a beam, that desire to rotate is just going to split the beam in half. So you saw a second ago, 10,000 pounds of moment. Notice a 1.5 inches wide by 3.5 beam can only handle 702 pounds of moment. That'd be bad to stick that beam in there, right? And all the 1.5 inch wide beams, even if they're 11.25 inches tall, only make it to 6,000. But if I get down to this beam, would you agree that's the first one that works? Can you see that, by the way? Is it big enough that you can actually see the numbers? Notice that's a 1 3/4 by 14 inch. So 1 3/4 inches wide by 14 inches tall. That can handle 13,000 pounds of moment. And so I could spec that beam to do the job that we just saw a second ago. Notice there's some thinner options, 3.5 inches wide by, there's another one right there. That says 13,000. So that's 3.25 by 9.25 right there. That's the size of that beam. Like that would do the job too. So it's a little wider, but not quite as tall. So it just depends on which one that I want. But that calculation is huge. And that's what chapter 4 is about. How to figure out what that moment actually is. And we're going to do it not with thousands of forces pushing down, but just a couple of forces pushing down. Any conceptual questions about that before I kind of simplify this down to something we can actually calculate? You feel like you understand what the gist of what I'm saying?
I'm curious for Boise Cascade, do they test each type of beam that they make, or do they calculate it?
That's a wonderful
and just
question.
Test a few of them?
Yeah, what they're reporting in this chart that I'm showing you here is what their beams are capable of doing. And I've been through that plant because I used to take my construction students through it. There's actually 2 Boise plants in the country, and one of them is in White City, and the other one's on the East Coast. And I had a kid in my class whose dad was chief engineer out there, so I got us in for tours, and I'd love to take you guys through that, but he's retired, so I don't have any contacts anymore. But no, they test them constantly. And by the way, just as a side note, this beam right here that I was just referring to says it will handle 13,000 pounds of moment. And so when they test it, it'll handle more like 20,000. In other words, they're promising that it will hold 13,000. So it darn well, since there's, all different kinds of wood and glue and so forth, and, maybe they built it when it was too cold or whatever, they're guaranteeing it'll hold 13,000. So does it make sense on average it would hold a lot more than that? Because remember, we're talking about people's lives here. Like, you can't get this wrong. You're an engineer. So yeah, they're testing them constantly. Like every shift, they're testing a kind of a sample survey of some of, if you've had statistics, just a survey of some of the beams to see how they're working. So that then they can kind of say, yeah, all the beams are working okay up to spec. This new glue is fine. Or because they're buying the glue from some other country, so they don't know, or some other company, they don't know if it's still good. So yeah, they're testing it all the time because of the liability of kind of getting this wrong, if you will. That's a great question. So yeah, materials testing is a huge part of kind of what you do. What else? Well, let me give you a little simple introduction. Again, you've had physics and it's a prerequisite. And so I am going to kind of ask you a little bit as we do this. What do you already know about this? Because I'm actually not sure. It's been so long since I took physics. I don't really remember. So my guess is this, and I'm going to say chapter 4 notes here. And you may notice on the syllabus, we're covering like the first part of chapter 4 this week and the next part of chapter 4 next week. So it's sort of 2 weeks in chapter 4. My guess is it was kind of introduced to you like this, kind of with a teeter-totter. Like if you have a teeter-totter here and you've got, say, a 120-pound kid up here, and let's say you've got a 180-pound kid over here, which one of those, what's going to happen to that teeter-totter? Is it going to go down to the left or down to the right?
Down to the left.
Maybe down to the left.
Oh yeah, depends on where the middle section is, right?
Yeah, so let's say this was a distance of 6 feet. And this was a distance of 5 feet. Do you understand that that matters? It's not just weight, it's also how far apart they are. I think I said that backwards. Do you know something about this from physics? I don't mean, are you awesome at it, but is it like, yeah, we remember looking at that a little bit now. Torque, which I just spelled wrong, is basically a measure of an object's desire to rotate. And as I said a second ago, if you have a beam that's sitting here and it's supported, and I'm actually going to start showing you how this stuff is really drawn. It's supported simply. Does it make sense that effectively the beam wants to crack in the middle and this side wants to rotate down? And so the beam is, if you look at a beam supported like that, you don't really notice it, but the beam is actually sitting there all day, every day going, like fighting against forces that are on it. You understand that? Like it's working. Right now, my arm is working to hold this pen up. I'm having to struggle, depending on the size of my bicep, to hold this up. And so even though I'm just sitting here and everything is static, does it make sense? The pen is working on me and I'm working on the pen. That's Newton's laws. For every force, there's an equal and opposite force. For every action, there's a equal and opposite reaction. If it's static, pen's pushing down, I'm pushing up. So that beam wants to rotate very badly. And you got to understand that as an engineer so that you can make sure you choose a big enough beam so that it won't actually rotate, split in half and rotate. And you may remember that torque equals, what does it equal? Do you know? Again, actually, did you study this in physics? What's the formula for that? What do you do with the weight and the distance?
I think it's distance cross with force, R cross F.
Do you know that from physics?
Yeah, that's what I remembered from physics.
Yeah. Put simply, it's really a force times a distance, but it's very important. Note, force has to be perpendicular to the distance. And I'll show you what I mean by that in a little bit later. So in other words, the kid on the left, his torque is equal to his force. Notice pounds is force. In metric, the force would be in newtons, but it's 180 pounds times the distance of 6 feet. So what would the units be then for torque?
Foot-pounds?
Foot-pounds. It's kind of a weird unit. Or in metric, it'll be Newton meters. Newtons for force and meters for distance. Those are the standards. So basically, the kid on the left is the teeter-totter, if you will, is desiring to rotate, has sort of 1,080, not pounds, but foot-pounds of desire to rotate, because the unit's got to include a force and a distance. What about the kid on the right? Kid on the right, his torque is 120 pounds times 8 feet, which is 960 foot-pounds. So now you know. Now you know what's going to happen. Now, do you understand this is not static? So I'll say this right here. Hence, this is actually dynamic. In other words, if this is a bridge, you screwed up as an engineer because it's rotating. Like we don't want stuff rotating. We don't want it moving left and right, up and down. We want it to balance, and we do not want it rotating. And so since the left kid is causing more torque, then effectively this whole system is going to have, let's see, what is that? Counterclockwise. It's going to have counterclockwise rotation. So we got to be able to figure that out. There's different forces acting on it. Notice this is a 2-force system, real simple. Not like the beam that I showed you a second ago that had hundreds of forces. So this is gonna, and notice it's close. Does it make sense these two kids would be able to teeter-totter just fine by like pushing their legs on the ground? Like they're pretty close. This is reasonably close. So engineers call torque moment. And there is a subtle distinction, and I read about it once, and now I can't remember what it is. But that's why you saw in that sheet, engineering sheet that I just showed you, moment, the moment on this beam. And I didn't stop to show you that, but it even labeled it as foot-pounds, just like we got here. It's a force times the distance. So you need to be able to figure out the sum of the forces on something to see if it moves left and right, up and down. You need to figure out the moments to see if this thing wants to rotate. And of course, your job as an engineer is to then come back and stop that. You got to do something that can stop that. That's the logic of rotation. That's the logic of chapter 4. Now, let's get serious about this. And I'm going to show you a practical and somewhat actually challenging example of this. Come on. So here's a humorous picture, a memorable moment for Dave. As I may have told you before, I'm a mountain biking enthusiast. And can you picture what's happening to poor Dave there? Why is Dave in this predicament where about 1/10 of a second later, his face is just going to plow into the dirt? I don't know about you, but I wish this was a video and I could hit play and watch what happens next. Type in mountain biker fails in YouTube and you'll see plenty of this. Can you see what's happening there? What's he trying to do? Like, why is he in this predicament? Can you, what's the ground he's on there? Can you see that? I don't know if you can tell.
And
There's a jump right here, and he jumped, and then see this little swale between it right there. He was trying to jump over the top of this and then land on this little downhill over here, but he came up short. Can you see that? And his wheel, you can see the dirt kind of hopping up right there. His wheel hit right there. And then when his wheel hit, his front wheel stopped, but his back wheel did not stop. Does that make sense? Can you see the vectors that I drew in there? Basically, he has a weight as he's flying through the air, doesn't he? And as long as he's flying through the air with no other forces acting on him, great. He's just flying through the air. But as soon as he hits right there, then all of a sudden his center of mass, remember he's a particle, he's him plus his bike. Maybe his center of mass is kind of on this line somewhere, that force line. And that is a distance away from where it hit. And so maybe this is 3 feet away, and that force is, say, 200 pounds times 3 feet. There's a force in a distance. He has a desire to rotate. And so he started rotating, and now his face is going to go on the ground. It's awesome. Love the sport. As I said, this should ruin your life in the sense that when you see things in the world, like this is how you explain them. Why did that guy crash? You know what's going on. It's actually fairly simple explanations, but you're not going to understand it unless you learn some things. So I said here, and I'm going to
I have a question.
Go ahead.
Will we go into enough detail that we could tell how much he would need to brake to counteract that rotation? Because I went to the dunes with my husband and some friends of his bikes, and one of them used to be like a BMX rider, and he was and how to do like brake check in the air in the middle of a jump to like level yourself out before you hit the ground again? Will
That's
we?
right. To some extent, yeah. I mean, I'm not going to look at that specific of a question, but yeah, because our goal is ultimately to solve this or to stop it. In his case, he was going too slow, and he's not going to fix that because he landed kind of on the uphill of something. Whereas if you jumped something and just landed on the flat, if you landed on the flat, the issue and what you're talking about is you came off the jump, and because you were leaning forward, you slowly started rotating like this. And if you're in the air too long, then eventually you just hit your nose and flip over. If you're lucky, you don't hit too late, and it actually levels out, and you're okay. So yeah, that's exactly right. So I'm going to give you a problem now. So here's a picture of, we'll call her Amy. And what I'm going to do is make up a bunch of numbers about this and see if we can actually figure this out. And fortunately, the book problems are actually even a little bit easier than this, which is kind of good. Again, I just think if you don't have a chance to actually try to formulate this stuff for real, then it's kind of really hard, I guess. I don't know how else to say it. So what are all these arrows? So first of all, with respect to the contact to the ground, does it make sense that you're going to contact the ground here and here? That's where the wheels are going to touch the ground. So in a sense, I'm imagining her back tire is kind of hitting the ground right now. Does it make sense if she hits the ground, her bike's going to rotate down, and then hopefully she'll be able to ride away and everything's okay? Like, this does not look like a crash. This looks like probably things are going to be okay. What does this arrow up here represent? What does that arrow represent?
The system center of mass, or maybe just her center of mass?
Well, this point right there represents the center of mass.
Oh, with the arrow going there. Okay.
And do you agree that looks reasonable? In other words, the bike weighs about 30 pounds and maybe she weighs 120 pounds. So the whole thing weighs 150. And the center of mass would be somewhere in the middle of her somewhere. So I just kind of drew that in there to kind of take a guess at it. So let's do this metric just to see if we can figure it out. Let's give her, say, 120 newtons of force based on the speed that she's flying through the air and so forth. She has 120 newtons of force, and notice it's at some angle as a result of the fact that she's flying through the air. So basically she's touching down right now. And so I'm imagining, as I said, her back tire is hitting the ground. So let's see, let's give this an angle. Let's see, what angle am I going to give you? Let's just do it to the horizontal. And I don't know, that looks like about 28 degrees maybe. So let's say she's coming in, the vector is at a 28-degree angle. And so from the last section, does it make sense you understand now how to break that into horizontal and vertical forces? And let's further give this distance. Let's see, let me just add a couple of notes here. Let me stick center of mass back in there. Let's say that distance, I should be using a different color than red because that's the same color as her pants, but let's say that's 1.6 meters. So roughly 4 feet. I mean, again, I'm just kind of guessing. That seems like about 4 feet to me. I don't think in meters very good. And let's see, I don't know if we know everything we need, but let's just mess with this a little bit. So does it make sense to you that this point right here is kind of the point of rotation? So she's hitting the ground right there is what I'm basically getting at. Now, would you say there is a force at a distance from that point that is causing her to want to rotate forward, that her bike's going to kind of chunk down in the front when she hits right there? Like, remember up to this point, she's just flying through the air like that with her front wheel a little high. She's just flying through the air, but then when the back end hits, it's going to go stop, and then that's going to cause the rotation. Does that make sense? So, but what I said though is the problem is the force has to be perpendicular. Does it make sense? I'm going to erase this, but does it make sense that, remember, vectors can move, so that vector's here. Would you agree that that right there would be the distance that's perpendicular? It has to be perpendicular. I can't come up with this distance. That's not the distance. The distance has got to be perpendicular. And so, wow, this is really confusing. Would you agree with that? How am I going to get that distance from this picture? That seems really confusing. Well, the easy way to do this is to do what we did in the last section, which is actually convert this from kind of a, a 28-degree vector. Let's convert it to, let's see, let's convert that to horizontal and vertical. So there's our force, 120 newtons. And so the kind of things I want to be able to calculate is I'd like to calculate the force horizontal and the force vertical from chapter 2. Could you do that now? Can you use the 28 and the 120 to convert force horizontal and force vertical? Do you see that as easy? I think the answer to that is yes. So in this picture right here, that would be my force vertical. Notice the arrowheads. That would be my force horizontal. And it's just trigonometry. So I could say, since the hypotenuse of this is the 120, I could say for the vertical one, the sine of 28 is opposite, which is force vertical over 120. Oh, okay, so I go 120 times the sine of 28, and I get 56.3. I'm not going to worry about rounding right now, but I'm going to say 56.3 newtons and kind of note that to myself. That's how much of her force is going horizontal. And similarly, if I said the cosine of 28, that would be adjacent over hypotenuse. So 120 times the cosine of 28. So I get 105.95. So I guess I'll call it 106. And remember, if I took 56.3 squared plus 106 squared and square rooted it, I should get 120, right? So now I have horizontal and vertical components of that force. Now, let's simplify things a bit. I don't know about you, but I'm still wondering, how am I going to get sort of these distances? Like, now that, would you agree that really is perpendicular? So that'd be like the distance vertical right there. How am I going to get that distance vertical? How would I know that? So what I'm going to do is simplify this a little bit to make my life a little bit easier. Just so you understand what I'm drawing, I'm going to stick those two wheels in there. So again, this is much harder than kind of your book problems. And I'm going to say this is her center of mass. And I was given in the problem that this was 1.6 meters. Do you agree with that? And now I've got to be given some other stuff that I didn't know before. So let's let's be given some other things. Like, let's say that this angle up here is 22 degrees. I'm making this up. Like, this problem did not have enough givens. There's more things that you'd have to know. And let's further say that, let's see, let's just do this to scale. Let's say this is like 0.5 meters, that length right there. And this looks a little longer, so I'll call it 0.7 meters. So in other words, what that's telling us is where is the center of mass? I got to know where the center of mass is. And so relative to the 2 places the bike hits, that's what I know. Of course, my drawing doesn't look like that, so I'm going to move it. So this is 0.5 meters, this is 0.7 meters. But here's the hard part. What angle is this force at? Would you agree it's not 28 anymore? What would it be? Any educated guesses? So look at the picture. Didn't this basically rotate down 22 degrees? I just rotated the picture because I'm a little confused by what's going on here. So isn't that going to cause this to rotate up 22 degrees?
So it would be 50 degrees.
Exactly. So it'd be 50 degrees. So what this is going to do is simplify my work a little bit. Again, what I'm trying to do here is help you conceptualize something real. We're going to do easier problems in a little bit where you don't have to do all this rotation. The problems you get in the book will look more like this, like they're already kind of sitting still.
Well, you need to find the new horizontal and vertical components.
That's exactly right. So what I'm going to do is go back and redo these under this easier regime, if you will. I'll change colors. So, and I will draw this in here. So that would be the force horizontal. This would be the force vertical. And those need to be drawn in the picture, and I'll show you kind of why in just a second. So 120 times the cosine of 50 is 77.1. And 120 times the sine of 50 is 91.9. So by breaking this into horizontal and vertical components, now it's really easy for me to tell what perpendicular distances are. Would you agree that I can move forces? Now, remember, remember it's important to realize this is the point of rotation. Is that what I called it before? Yeah, point of rotation. POR. And so that does make a difference. So, moment. Well, one, I have force H. So I have force H times how far, it's very important. How far is force H away from the point of rotation? What's its distance? torque or moment is the force times the distance. I have the force, that's 77.1. But how far away is it? Remember, vectors can move. Would you agree that's also force H? This is a very important concept. It sort of doesn't matter where it is. Now, you can't change the angle, but it can be anywhere. And so would you agree that distance right there, this distance right here, is its distance? In other words, you don't want this to be the distance because that's not perpendicular to the force. And it's also hard to figure out. That distance right there is 1.6. I'll remind us that has to be perpendicular. 1.6 meters. If I take 77.1 times 1.6, that's 123.36. Newton meters of moment, desire to rotate. Which direction is that causing the bike to want to rotate? Is the bike wanting to rotate clockwise or counterclockwise? Notice this force and that distance is going to want to cause rotation in this direction. That's counterclockwise. So this is counterclockwise. Do you agree with that? You seeing it?
I'm a little bit confused about the distance though. Wouldn't it have to be the distance between the center of mass and then where our bike wheel touches?
Well, it does if you want to leave the force just this force over here. In other words, you just say, I don't want to break it into two forces. Then I have to use this force over here, and then it would be perpendicular. And so you'd have to figure out what that perpendicular distance is. But I'm breaking it into two separate forces. And this is why this is not obvious, because I'm glad you're questioning this, Ben, because this is not obvious. So I've only looked at the horizontal one, and because vectors can move, because they can be anywhere, didn't we do that in the last section? We moved the vector and put them head to tail. We moved them around to see where they were. Doing the same thing here. If I move it to the position of that blue one, then it's clear to see that that distance, and notice it is, Ben, it is 1.6 meters from the center of mass. Isn't that blue arrow still pointing at the center of mass?
True. So
that is important.
let's see. Okay.
So how am I going to get the since there's a second force here, how am I going to get the force vertical times its distance? Maybe I'll say distance horizontal, distance vertical. How am I going to get that to happen? And this is exactly what Ben is asking. Is this it? Is this where that vector is, force V right there? The answer is no. It's got to be pointing at the center of mass. And so in a sense, I actually have to move this one. Really, force vertical gets moved over here because it's got to be pointing at that center of mass. Again, I can move it as long as I don't change the angle. It's like wind, it blows everywhere. How far is that force?
Would that one be the 0.7 meters then?
That's
If you
exactly
can move
right.
it down along that same line.
That's right, because it's kind of going in this direction and it's got to be perpendicular. Then that is distance vertical. 1 point is 0.7. So we said that force was 91.9 times 0.7 meters. 91.9 times 0.7 is 64.33 Newton meters. What direction is that causing? Is it causing clockwise or counterclockwise rotation? Again, around the point of rotation or point of reference. Again, notice it's going this direction around that point. Isn't that causing rotation around that point in that direction? Hey, that's counterclockwise as well, isn't it? So they're working together. They're not working against each other. If they were working against each other, we'd have to subtract them. Because they're working together, then the moment, and I'm going to label this P, point P for point of rotation. The moment around P as a result of this biker's weight and the angle at which they hit the ground at is the sum of those two, which is approximately 187.69. So maybe based on just common sense, you say, you know, here's the ground and here's the stick that's falling down. When the stick hits the ground, dunk, then it's going to rotate to the ground like that. That's what the spiker's doing. They're flying in, the back end hits, and then they snap to the ground like that. Now, on a real bike, you might snap to the ground so hard that the bike goes forward like this and you go over the handlebars, which is one of the major things that goes wrong on a bike. But do you see the math here? Like, that's how badly that's rotation is happening. Does it make sense that rotation could buck the rider off the bike? Do you see how we broke it into its component forces and moved it around so that they were perpendicular? I mean, that's kind of the concept here. So there's more than one way to do this. There's some automated ways. Ben alluded to this called a cross product, and we'll get into that next time. But today I just want to stick with stuff that makes all kinds of sense. Now let's just do anything about, I want to just do another example of that now that's easier, like a book example. I wanted that one to be a little bit more fun and introductory, if you will. I think I'm going to erase this, but on a side note, nah, I don't want to say that. I don't want to confuse you. Let's bring in another book example. Stare at that picture. Just like the last time, this is two different forces. So this is like a flagpole or something, and there's a worker. Apparently they're a worker because they got a hard hat and overalls on. If you got that on, you're a worker, I guess. So I need to make you guys bigger. So notice the two forces are P and F, is it, I guess? Man at B exerts force of P, 30 pounds. So you can tell that, in a sense, this is the point of rotation down here, like it's going to rotate around that. Does it make sense that the person at B is pulling on it in such a way that it wants to rotate that way? In other words, counterclockwise. Whereas this person over here is pulling it, it wants to rotate the other way clockwise. And so does it make sense if they're equal, then it'll stay static. But if one's more than the other, then it's actually going to, you know, get pulled over or something to that effect. Does that make sense? But there's only two of them, so this isn't hard. Now, what do I mean by that? Well, you could make this really hard on yourself, which is to move this. What did we were told this was a 30-pound force right here. You could move it down to here, in which case that would be your distance. But do you agree that's the hard way? Because I'm not sure how I'm going to figure that out. Can you? Absolutely you can. But it's so much easier to convert that 30-pound force to its horizontal and vertical components. Do you understand that? because then the distances are just in the problem. See how there's a 6 feet and a 12 feet? Like those distances are going to be the distances I need. And so it's easier to convert the forces to be perpendicular to the distance than it is to convert the distance to be perpendicular to the force. But they both work. I won't do this, but perhaps you're good enough, because this isn't a terribly hard problem. Perhaps you're good enough to say, well, isn't this whole thing right here 18 feet tall? And so if this is a 45-degree angle right here, then so is that. That's a 45. And so if this is 18 and that's 45, can't you do trig and figure out what that distance is and then just multiply 30 by that distance? It's not hard. If you find that interesting, you might take that approach. But what I'm going to show you is what I consider to be the easier way to do this. And so if I draw both components in, you go over there. Isn't there a horizontal component? And again, here's the, like, you want your work to speak to you. And by the way, when I hire an engineer to do the calculations on my houses, one of the things that has to get turned in is their calculations, and people need to be able to read them to check them. So since that's P, I'm going to call this P horizontal, and this would be P vertical. Do you agree with that? And so since this force itself, I'll move this over. I'm just going to erase it, I guess, since I can't seem to move it. Since this force is actually 30 pounds and that's a 45-degree angle down there, then that means this is also a 45-degree angle. You agree with that? And so I could say, again, I want to try to do my work in sort of an organized way. So I got people B and C. So I'm going to say B, and now I'm going to do all the work for B guy. And I want to find P of H here. So I'm going to say P of H. And now here's going to be my work. So I can see that if I said the cosine of 45 degrees is P of H over the hypotenuse, which is 30, that's going to give me the horizontal component. So 30 times the cosine of 45, I get 21.21. So P of H, and I'm telling people I'm rounding this off, is 21.21. Notice again, I'm not really paying too much attention to rounding right now. And that would be pounds. Maybe I should write that in there. So 21 of those 30 pounds are horizontal. And to make a right triangle, I would actually have to move, if you will, P of V over here. And so maybe it's easier to see if I draw that right triangle. So then I could say, okay, what about P force vertically? Well, that'd be the sine of 45 is P of V over 30. And in this case, I get the same exact answer because 45 is symmetrical. And you also may notice I haven't even really read the question yet. I don't even know what they're asking me. I'm just figuring out stuff that I can figure out. I'm sure I probably will be answering the question. But now I'm going to move on, reminding myself that M is what I'm going to use for moment. What about the moment as a result of the horizontal? So I'm going to move this down since I can. What about the moment horizontal? Remember, that's a force times the distance. Well, now I know its force, 21.21. But what's its distance? How far is P of H from the point of rotation? Do you see how it's easy to steal from the picture? Blurt it out. What's the distance? How far is that away?
18.
Yeah, here it is, perpendicular straight down, 6 feet plus 12 feet, 18 feet. So 21 pounds times 18 feet. So 21.21 times 18, I'm getting about 381.78. 381.78, I think I'll call it 8 foot-pounds. And again, can you see that that's also trying to rotate this counterclockwise? Now you may remember from trig that counterclockwise is considered to be positive, so you could just leave it positive and assume people know that. And if it goes the other way, you could call it negative. But it is important to understand when two rotations are working together versus working against each other. So I'm saying counterclockwise, but I could just be using the convention of positive and negative numbers. That'd be okay too. What about the moment vertical as a result of this vector? It's kind of a trick question. Do you know what I mean by that? What's its distance?
Would it be the distance between point B and the vertical line that connects with A? The
Notice
horizontal connect.
it's easier than that. Where is it pointing? It's pointing right at the point of rotation, which means there is no distance. It's pointing right at it.
Okay.
So it's actually nothing, 0 feet. Now last time each contributed something, but this time that one's pointing right at it, so it doesn't make any difference. So you can now see, thanks to B guy down there, that pole wants to tip over to the left. And now I got to kind of look at the other person. What do I know about that? Let's see. Determine the magnitude of the force the man at C must exert. Oh, that's interesting. So they didn't tell me how hard he's pulling. Does that make sense? So they didn't tell me. And they said, what's the magnitude for the man at C to prevent the pole from rotating? So in other words, if we want this to stay static, does it make sense this desire to rotate counterclockwise, which is 381.8, the other person better produce 381.8 going the other way, and then it'll stay still. So this is kind of a good statics problem because, you know, they're trying to keep this thing up in the air. Notice the angle. How is the angle given? What angle is he pulling at? Well, notice it's given as a ratio this time, which is all trig ever was, as a ratio. Cosine is the ratio of the adjacent side divided by the hypotenuse. That's actually easier. If you like angles, you're more than welcome to go inverse tangent of 3/4 to come up with what the angle is. But again, my job is to break these into their two components. So I'm going to switch to blue. So because that person is pulling at that angle, that would be the force horizontal. And just like the other one, this is what the force vertical is going to be. Notice force vertical is pulling right at the point, so it's not going to contribute anything. So notice how clear my work is. Now I'm switching to C. All the work about B is done and it's up there. The one thing that's really missing up there though is probably kind of a conclusion from all of this. And I should have put this down here because that was their calculation. I don't think I could ever use paper and pencil again. I love this. So as a result of all of this, really that's our answer. Like of all the work I just did up there, that's the thing that I need to pay attention to. That's the one I need to know since it was really those two added together. So what's going on at C? So the moment, let's see, what am I calling this? The moment horizontal. Notice I'm back to the moment horizontal again. Somebody think about this. I already used moment horizontal. So now I got two things moment horizontal is equal to. How could I have distinguished that a little bit better?
M sub C8.
Yeah, maybe something like that. Like back here, I could have said M sub PH or something like that. Notice it's kind of weird. Like if you really wanted to speak clearly. Now, I personally don't like to see more than one, two letters like that. It starts to get confusing. So, you could name them 1, 2, those kinds of things. Or I could have called it B since it was like Guy B, the B person. So I could have said MBH. So I didn't even notice that was a problem until just now, if you will. So I'm going to call this MCH, I guess, since it's person C. It's like sub. Well, that's his force, which is force horizontal, which I don't know. How far is force horizontal away? Perpendicular? How far perpendicular is it from that point of rotation? You're seeing it here, straight down 12 feet. Notice I actually don't get an answer for this because they didn't tell me what his force was. Moment around C vertical is going to be force vertical times 0. So that's going to be 0. So does it make sense then in conclusion that I really need force H times 12 to be equal to 381.8? Do you agree with that? Because this person is pulling the other direction, which as we said is actually clockwise. So they're pulling against each other. One will be, if you want to add them, one would be positive, one would be negative, and they would add to 0. Or in my case, if I label them as clockwise and counterclockwise, then they just both need to be equal. So based on that algebra equation, I say, oh, okay, cool. All I have to do is divide 381.8 by 12. And I get 31.82 approximately. Did I answer the question? I didn't. Do you see that? I found out how hard that guy would have to pull horizontally, but he's not pulling horizontally, right? So let me show you a better way that I could have done this. And I'm purposely going to kind of cross this out. Well, I won't cross it out. I can just add to it. Based on that right triangle, what fraction of his pull is horizontal? Based on the 3, 4, 5 triangle, what fraction of his pull is horizontal? Four fifths. Does that make sense? 4/5 is horizontal. So a better way to say this would have been to say 4/5 of the force, not the force horizontal, the overall force. Whatever force he's pulling on at the angle he's pulling at, 4/5 of it is horizontal. So switch to red. Better would have been to say 4/5 of the force times 12 equals 381.8. So I'm dividing by 12 and dividing by 4/5. And I get 39.77 for the actual force. Again, the back of the book is going to call that 39.8, right? 3 numbers. So how come he has to pull so much harder? The other guy was pulling at 30. How come he's got to pull so much harder? Just at a glance, just the feel of the problem. Because his rope is attached lower. His lever arm distance is smaller. Now his angle's a part of that too, the angle he's pulling at and so forth, but his rope's attached a whole lot shorter, so he's got to pull harder to achieve the same thing. How does that feel? I think I've answered the question now. Notice it says the resultant. That word needs to mean something to you. The result, the resultant moment about A. Notice they're telling me what I just assumed from common sense. It's going to rotate around A. I can just tell by looking. So that result about A, the both forces, is 0. So in my case, I set them equal to each other, but I could have called one positive and one negative and added them up and set it equal to 0, and that would have accomplished the same thing. And by the way, that's often easier. But again, what I'm trying to get across is kind of a conceptual understanding of this, not just a mechanical understanding. I want you to understand the concept, the logic of it. So let's take a look at one more, also somewhat realistic example that's very much like this. Let's see, am I getting done what I need to get done today? Yeah, I think so. And I'll give you a second to stare at this one instead of just immediately doing it for you. It's one of my favorite devices in our culture. Have you seen that in the real world? You don't see it too much in Medford, but if you go to bigger areas, these things are just awesome. And again, this guy Hibbler does a pretty good job of drawing pictures, but can you appreciate that that's a very precarious structure? And it's like 10 stories up in the air a lot of times. And again, go Google search crane fails, tower crane fails, and watch them like fall across the city and smash cars. And actually last year, a tower crane fell in, I think it was Seattle, and it smashed a car and killed the person because they got it wrong, and it momented, it rotated. And so it wasn't static, and bad things happened. But can you see all the stuff here that wants this thing to rotate? Like just at a glance, without reading the question again, I see a weight over here. And of course, doesn't it obviously want to rotate around A? And so does it make sense that that weight is going to want it to rotate to the right, which would be clockwise? And I'm going to call that negative rotation this time. Rather than write down clockwise and counterclockwise, I'm going to say that wants it to rotate negatively. Is there anything in that picture that's going to stop that from happening?
There's the counterweights over on the left.
Yeah, see those counterweights? It looks like there's 2 of them. Looks like there's G2 and G3, like a couple of counterweights. And so they're on the left side of point A, and they're going to want it to rotate the other direction. And so those are offsetting each other. And so the brilliance of this design is that counterweight right there on a tower crane can actually move. And so they can move it into the right position so that it balances. And so it's actually a balancing act. That thing is not strong enough to lift weight. It'll tear the whole thing down. But if you get the weight pushed out on the left-hand side, then it can. And so notice here, it looks like anyway, this G3 is fixed in place, whereas G2 looks like it could slide on a trolley. And so this counterweight is probably just counteracting the fact that, you know, this always has a load over here, right? And so this is like helping permanently, whereas this is helping depending on how far away it is. Again, I haven't read the question. I'm just kind of thinking about it. And notice I'm given all kinds of measurements here. This one is 12.5 meters away. This is 9.5. What the heck is that? 9.5 to what? G1. What's G1? They're acting like that's a weight. Why is that a weight? I don't see anything there. What is it?
Must be the center of mass of that the right part of the crane.
Exactly. Like that thing's not zero. Like it's got weight. Remember the beam I showed you a second ago? The self weight, like the beam has weight. That crane is probably the center of that boom arm sticking out there. And so anyway, let's go tackle this. Tower crane is used to hoist. Ooh, here's something important. What? It's hoisting what size load? Did you read chapter 1? I know Aaliyah knows this. Megagrams, not kilograms, not 1,000 grams. How many grams is that? What's mega?
A million.
Million. That's million grams. And so it's 1,000 kilograms. That's 2,000 kilograms. Does that make sense? If you, or 2 million grams. And so that's interesting. Let's see. And as I glance at it, notice all of them are megagrams. And that sort of makes sense. This is heavy. Like we're not lifting grams. This isn't some teeny little thing. So the tower crane is used to hoist up a 2 megagram load. So we're told this over here is 2 megagrams. Do I want to leave that in megagrams? I'm not sure. The standard unit for torque or moment is Newton meters. And so a Newton is a kilogram meter per second squared. And so there's part of me that thinks that should say 2,000 kilograms because if I want to use Newtons, but maybe the problem doesn't care. Maybe I'm not really sure. I'm going to go back and fix it if I feel like I need to. For now, I'm just going to leave it alone. So notice I know everything I need to figure out that force. So I'm just going to say here the sum of the moments, and I'm just going to start into it. So if I say 2 megagrams, and as I think Aaliyah said the other day, it's very important that's a capital M, otherwise it's milligrams, and that'd be a huge mistake. 2 megagrams times 12.5 meters. Isn't that a torque? A torque is a force times the distance. Wait a second. Grams are not force. Do you understand that? Metric force is not force. That's not good. Who knows what to do? A Newton is equal to a kilogram meter per second squared. That's a Newton. That's force. That is only a mass. You understand that? What's Newton's law say about how to get force out of mass? What do you got to do to force to get mass?
Multiplied by g, the acceleration due to gravity.
Exactly.
Yeah.
Newton's law, second law says force equals mass times acceleration. So I've got to take 2,000 kilograms times, what's the acceleration of gravity in metric? Chapter 1. What is it? And you should know it from physics. If you don't have this memorized, I'm going to call Dusty and tell him to lower your grade 1.
9.8 meters per second squared.
Yeah. In this class, in chapter 1, though, because we're working to 3 significant digits, it's 9.81, which is a little more accurate. So cross that out. 2,000 kilograms times 9.81 meters per second squared is 19,620 newtons times 12.5 meters. Tricky, isn't it? Our system pounds our force. Metric, you got to turn it into force. And the subtle reason for that is because if your if your mass is more of a measure of like volume, And if you're on the Earth, then the Earth has a gravitational pull of 9.81. If you're on another planet, something else. By the way, if you're further away from the Earth, then that pull is less. Do you understand that? That's also talked about in chapter 1. But, close enough. If you're on Earth, that's the number you use. So it's trickier than it would look. Make note of that. Is that a positive or negative rotation? Since it is trying to get it to rotate around A this way, do I call that positive or negative in your understanding of trigonometry?
So that would be negative then, right?
Exactly. We said that counterclockwise was positive and that clockwise was negative. And so this time, rather than writing clockwise and counterclockwise, because notice I have a whole bunch of them. I have like 4 of them. So that's actually negative. So I'm going to write that in black, kind of highlight it. Okay, I knew the force and I knew the distance, and so I multiplied it out. Great. So I got that. What else do I got? Do I have other things that I know? Let's see. They said the 1.5 megagram jib, and notice they don't expect you to know what a jib is. They said BD. There's B and D. Oh, that's that arm that's reaching out. That's what it's called, by the way, is a jib. That jib is reaching out there, and I'm told it's 1.5 megagrams. So little side note over here, jib. 1.5 megagrams. And by the way, maybe you can't do what I just did in your head a second ago. So what I'm going to do is do this the sort of safer way. There is 1,000 kilograms in 1 megagram. I would need to look that up. That would cause megagrams to cancel, and I'd have whatever that is, 1,500, I guess, 1,500 kilograms. And 1,500 kilograms times 9.81 meters per second squared. Notice the 0.1 is actually pretty important. The 0.1 is 100th. 100th of 1,500 is actually 150. That's why you're more accurate in this world. So I got 14,715 kilogram meters per second squared, which is renamed, as I said, in newtons. Which direction is that trying to rotate? The tower, is it positive or negative? Same direction. It's also negative. So minus 14,715 newtons times its distance. And again, notice that distance is perpendicular. If I draw G1 in there, right there, isn't that distance perpendicular to that? So notice I didn't have to convert anything. These forces aren't going at some weird angle. Thank God I didn't have to convert them. So that's 9.5 meters, I'm told. So both of these components of this crane want it to rotate clockwise, negatively. So that's why they're both negative. Keep going. What else do I know? And the 0.5 megagram jib BC. Wait, I thought we already knew what the jib is. BC. Oh, BC, that's the left side. So that's the same material. It's just another extension. It's kind of the horizontal version of that crane. So is that G2? The 0.5 megagram jib BC have centers of mass at G1 and G2 respectively. So they're both 0.5. Is that what that's saying? Is that what you think it's saying? That's what I think it's saying. That's bothering me. Is that what it's saying?
No, that's the second half of the sentence. So the 1.5 megagram jib BD is that G1 center of gravity.
Yeah. So yeah, G1 was the one we just did a second ago. So no, they haven't referenced G3. That's down further in the problem. So I wasn't reading that very carefully. And then you're going to find that sometimes, like when you read these, they're sometimes easy to interpret they're saying. Really, they're just telling me that G1, no, G2. They're telling me G2 is at 0.5. That's what they're telling me, right?
Yeah, I think,
So-
are they saying that, yeah, G2 and that whole jib is kind of that combined center of mass is at 4 meters from the left.
Yeah, so G2. Do you agree with that? G2. So I'm looking at, notice I renamed jib G because now I realize there's two jibs. And again, I'm trying to just model how you think about these things and how you write your work. So if that's 0.5, that'd be 500 kilograms times 9.81 meters per second squared. 500 times clear is 4905. But isn't that causing rotation that's going in the other direction? Again, it's very important you see this. That's counterclockwise rotation, which is actually positive. So now it's plus 4905 newtons times 4 meters. Determine the required mass of the counterweight, C. Oh, we don't know that one. And that makes sense. It's just like the last problem. In other words, we don't want this thing to fall down, right? So we don't know what G3 is, but we do know its distance at 7.5. And we also know that it wants to rotate positively. So couldn't I say plus G3 times 7.5? Now, what about the 9.81? Does that need to be part of this? What are they asking me? They're saying determine the required mass. So if G3 is a mass, then to make it a force, then I'm thinking, yeah, I actually do need to do what I did on all those other problems and multiply that times 9.81 so that G3 it comes out as a mass, not a force. Does that make sense? It wants the answer in kilograms because it said mass, not newtons. If it said how many newtons is G3, then I wouldn't need the 9.81. So this is the load, this is G1, this is G2, and this is G3. And what do I want all of this equal to? All of those moments, there's 4 of them here. There's 4 different arrows. What do I want all that to equal? Nada. That's the backbone of this class. That's rather than calling some clockwise and some counterclockwise, it's actually way easier just to add them all up and set them equal to 0. So fortunately, I have an equation there that's only got one unknown. So all I have to do is turn the load G1 and G2 into numbers and then add or subtract them to the other side, and I'm kind of on my way. So just to go a little more slowly and just kind of make sure I don't screw up and to give you time to think about it. So 19,620 times 12.5 is 245, 250. That was negative 14,715 times 9.5 comes out. Oh, thank you for a negative for a decimal. Comes out 139,792.5. And then plus G3 4905 times 4 which is 19,620. Kind of an unfortunate coincidence that we had that number before. But the first one was newtons, and this one's actually Newton meters. And then lastly, I've got G3 times 9.81 times 7.5. Well, I can take 9.81 times 7.5. And if I do that, I get 73.57. 73.575. And I need that all to equal 0, which I'll squeeze in up there. So of course I can collect all those first numbers together, right? Negative 245, 250 minus 139, 792.5 plus 19,620. You notice how easy it would be to miss a button. I actually just looked back at my calculator, and 19,620, the 2 didn't show up. So, you know, the whole thing fell down because because it didn't show up. Like, you can't get this stuff wrong. So you got to check your work. You got to look back and see what you get. So I got a sum total of all that. I got negative 365, 422, which I'm going to add to the other side. So now I got 73.575. Gee, this should be like boring to you, like solving algebra equations. But if I add it to the other side, then I can divide that by 73, and I finally have G3. So G3 is, I got 4996. .66666. What are you going to see in the back of the book? And by the way, what are the units of this? Because this is not, like, you could screw this up and it would be fatal. What were our G's measured in? Well,
kilograms.
Notice I had all the calculations I did, and that's why I said this is not obvious. All the calculations I did had those in kilograms, didn't they? Therefore, this one's in kilograms too. It'd be easy to look at the original and say, oh, they were in megagrams, and so that's megagrams. If you get that wrong, the whole thing falls down. Do you understand that? Like, oops, sorry, my weight was 1,000 times too much, and the whole thing fell down. So I'm enjoying the fact that I was careful about putting all the units in now. So actually, this is in kilograms. What's the back of the book going to say? So that's right now, if I don't nitpick the details, which I'm not going to do on a test. But what's the back of the book going to call that?
Probably 4.97 megagrams.
Nice job.
Okay.
Technically. So we never want, you can't have a 4-digit, you can't get rid of one of the digits because that's a 4,000, that number is almost 5,000. You can't get rid of it, but to get it down to 3, you've got to move the decimal point over. If we move the decimal point over 3 places to the left, it becomes 4.996 and some change megagrams. But notice that 6 would cause that 9 to round up to 10. So the back of the book is actually going to say 5.00 megagrams, unless I rounded too soon someplace. If I rounded somewhere, maybe I'm off by a hair. Remember, the 0.00 is kind of cool because it tells somebody, hey, I didn't just round this to the nearest whole number. I rounded it to 2 decimal places. It just happened that they came out 0. So that's kind of cool information to add. And again, I'm not supremely confident that I didn't write something down wrong. And as a matter of fact, what's my calculator say right there? I didn't even write my number down right out of the calculator. It's 4.966, not 4.996. Does that mean I don't know what I'm doing? No. There's a lot of numbers here, like even if you know what you're doing. So I guess I'll go fix that. That was supposed to be a 6. So it's actually 4.97. In my case, you notice that's close enough that maybe the whole thing wouldn't have fallen down. I got lucky. My mistake was, if you will, kind of a minor one. On a test, if your work is clear and I can tell that your mistake was not a conceptual one, but it's sort of an accidental one like mine was, then I don't have to take very many points off. But if you get it wrong and I sort of can't tell why, then it's going to be harder for me to give you points. And, you know, in my case, it would have been a bummer if I kind of got a C on that problem. But remember, in the real world, does it really matter? If the crane falls down, does it really matter? Can you call somebody and say, hey, it was just a transposition mistake. I accidentally wrote the wrong number down. No one cares. Like, you're fired, you're dead, you're never working in engineering again. Like, you can't get this stuff wrong. You got to check your work. That's why it's good to have computers do things. It's good to not have to do all this stuff by hand, or good to have somebody else check your work and make sure they get the same answer you got. In my case, the only reason I caught that mistake is I just flipped to my notes when I did this last year, and I saw that I got 4.97. I was like, I wonder if that's just rounding, and then I looked up at the number I rounded and realized it wasn't the same, and it made me check. Otherwise, I would never have caught my own mistake. Torque or moment is not complicated. It's just a force times the distance. Where it's going to get complicated is, what if that force is in 3 dimensions and it's pointing not in one plane, but pointing off in some weird dimension? What if it's complicated? That's where these cool shortcut techniques of a cross product are going to come in, and that's what we're going to talk about on Thursday. But you should be comfortable going through a decent chunk of the assignment. I would encourage you to do that. Don't wait till Sunday night. Wait into the first part of, I'm looking at the
Also, it looked like on your calculator it was negative. Do we need to add in what direction?
Yeah. The only reason it was negative is because I don't know if you can see that, but I just left the negative number in there. So in my case, it actually shouldn't have been negative, because I had negative 365. When I added these numbers together, I had negative 365 for that. So that when I added it to the other side, it became positive. And I just thought, well, I don't want to rewrite that whole thing. I'll just know that it's actually supposed to be positive. So I took my negative answer and divided it, so it came out negative. All right, I'm going to post all these notes that we made today. I'm going to post the lecture. Just to make sure you're all tuned into this, because you're not going to get everything I say the first time. You're going into our communication, and you're looking at, not test review yet, but you're going in here and looking at these lectures. So we did these 3 problems in class last Thursday, and then here's the lecture that's after it. So I've got 2 or 3 things I'm going to post today, and then there'll be a 119 lecture after it. So you can steal any of that stuff you want if you miss part of a day, or something that didn't make sense. This takes more time. Like, you cannot watch me do this and then, oh, I got it, and you're done. Like, you're going to struggle with questions. You got to put your own thought into it, and there's no substitute for that. I can't make you do that. All right, get yourself out of here, or stay after if you want to ask me any clarifying questions. Always happy to start class, like for you to say, hey, before you start, can I ask you a question about something? And if I feel like that's a 30-minute answer, then I might say, let's stay after class. But if you have the question, probably other people do. And if I can say something quick about it, maybe in 5 minutes, then everybody would benefit from it. That's always a good way to start class. And I can pull up the problems that you're working on, and we can talk about them a little bit. Anything else?
Sounds good. Bye, Doug. See you on Thursday. Bye, everybody.
I'm gonna go grade your homework that you sent me over the weekend, I
good.
hope. I know I saw some of yours, but I can't remember if I saw everybody's.
Yeah, mine was kind of last minute.
I have it. I have yours now.
Yeah,
Mhm.
there's missing 3 problems, and I had a question if I should like turn them in partially
Absolutely.
done to get partial credit, or turn them in late finished, or
I would say both. Like,
okay.
I would say, especially if it's because you had a question, just write a note and say, this question's partially done. I had questions about it, but I'm not going to read that and then chase you down.
Right.
So if you stayed after class today, sort of because you saved it for the last minute, like you saved it for Monday night at 10 o'clock or something, and then you realized, oh, I'm stuck, now it's kind of too late to get help. I would still rather you ask me questions at some point and then finish it and turn it in. And for the most part, if that isn't some pattern, if that's not a pattern you keep, I'll probably give you those points as long as it isn't like a week later. If you jumped
Okay.
right on it and finished it, I'd far rather you finish it and give you points. So
Okay. Should we hop over to the office hours Zoom?
let's do it in case some of my calculus students show up.
Okay.
They don't know that I'm in this one. So yeah, let's do it.
All right.
See you in a minute.